And today's lecture, lecture number 5, we have already gone through the mathematical basics of GR and what we're going to use in order to describe the physics in GR. So today we come to exactly that. What is general relativity? Is the main topic of today, and we will start also with considering the basics. So you've all heard about space-time, but the question is, what is space-time? So this is the overlying topic of the first hour. What is space-time? So in special relativity, you are familiar with Minkowski space. So in special relativity, we have Minkowski space. Now, the question is, what sets Minkowski space apart from regular Euclidean space? Well, it's that we have, if we draw here, Minkowski coordinate axis, we usually put the spatial axis horizontally and the temporal axis as a vertical axis. We have this set of coordinates. If this was Euclidean space, we could do translations and rotations, and it wouldn't change the metric at all. But in Minkowski space, we instead of rotations, we are going to have the Lorentz transformations. So I'm going to be able to translate here into new axis t prime and x prime that are going to preserve the Minkowski metric. So this is a four-dimensional affine space, and the difference between Minkowski space and Euclidean space is that Minkowski space has a pseudo metric. And it's of signature 1, 3, rather than the metric of Euclidean space. So in this case, we will use the convention that the time-like direction is positive. So we will have plus, minus, minus, minus. This means that the temporal direction, the inner product, or rather the norm squared of a time-like vector is going to be positive, and the norm squared of a space-like vector is going to be negative. And as someone asked, I don't know if it was the last time or the time before that, in Minkowski space, we don't have a metric. What we have is a pseudo metric. So if you look back, what we said about the metric is that it should be linear, it should be symmetric, and it should be positive definite. When we talk about the pseudo metric, then we drop this requirement of having to be positive definite for the requirement of being non-degenerate. Which essentially means it's going to have 4 non-zero eigenvalues. And the signature here is answering the question, how many eigenvalues are positive and how many eigenvalues are negative. And with our convention, with a 1, 3, we have 1 positive eigenvalue corresponding to temporal directions and 3 negative eigenvalues corresponding to spatial directions. So what we can say about Minkowski space then is that it is the 1-3 signature equivalent of Euclidean space. So with that, I mean that it's a space which has this pseudo metric rather than the metric of Euclidean space, but it's flat and it is an affine space. So we're going to see many similarities between Euclidean space and Minkowski space. So if we just make that comparison, so if you look at the Euclidean space, we have certain transformations that preserve the metric of Euclidean space. Those are the coordinate transformations between different Cartesian coordinates. So we have translations, we have rotations, and we have the metric itself, which is then always going to be the Kronecker delta in Cartesian coordinates. And if we make the comparison to Minkowski space, the translations, well, in Minkowski space, we still have translations, but we have them both in the spatial and in the temporal direction. So we have spatial plus temporal translations. The rotations in general turn out to be what we call Lorentz transformations. So even a purely spatial rotation in Minkowski space, it's a type of a Lorentz transformation because it preserves the Minkowski metric. And so the metric in Minkowski space is this pseudometric eta mu nu, which is which in Minkowski coordinates has then the form 1 minus 1 minus 1 minus 1 and zeros on the off diagonal, and is conserved under both spatial and temporal translations as well as Lorentz transformations in exactly the same way that the regular Euclidean metric is invariant under transformations and rotations. So this is the Minkowski space of special relativity. Now, just as we in Euclidean space we were not restricted to using Cartesian coordinates, we can in general also use curvilinear coordinates in Minkowski space, and there's a very interesting set of coordinates which is called Rindler coordinates, which is a curvilinear coordinate system of Minkowski space. So just as we did with rotations, or sorry, with polar coordinates in Euclidean space, we can introduce the following coordinate system. So we consider the following coordinates. So I'm going to introduce them as x. I'm going to introduce as capital X multiplied by the hyperbolic cosine of some constant alpha multiplied by t. So alpha here is a constant with dimension 1 over time. And the time coordinate I'm going to write as capital T and then multiplied by the hyperbolic sine of alpha times, sorry, I'm still going to have the x here and the t inside. So this kind of reminds you of polar coordinates, right? It also reminds you probably of the homework set, but then we introduce these coordinates on Euclidean space. But here we're going to work with Minkowski space. So I'm now changing them from the Minkowski coordinates x and t to the new coordinates capital X and capital T. And if I do this, the metric tensor is going to be given by the line element ds squared, which in Minkowski space is dt squared minus dx squared. And if we perform this computation, what we end up with is alpha x squared dt squared minus dx squared. So just as we could compute metric components in other coordinates in Euclidean space, we can do exactly the same by by looking at the line element in Minkowski space for the new coordinates. So we would find then here that GTT would be alpha squared x squared, GXX would be -1, and GTX is equal to GXT equal to 0. Now, if we look at what part of Minkowski space this describes, as we discussed before, coordinate systems don't always describe the entire space. So if we take now the coordinates x to be greater than 0 and t to be, well, -infinity to infinity, then the region that we're going to describe with this coordinate system is going to be the following. So we are going to describe the region to the right here. So this quadrant of Minkowski space. And the coordinate lines here, we're going to have coordinate lines going out like this. And those are the coordinates lines of the t coordinates. No, sorry, that's the coordinate lines of the x coordinates, right? X coordinates. So it's the surfaces of constant t coordinates, and we're going to have the coordinate lines of the t coordinates. And now my drawing skills come to the task, but they look something like this. It's hyperbolae essentially that are these t coordinate lines. And you see the similarity here between the t coordinate and the polar coordinate in Euclidean space. It's essentially telling us where on a particular hyperbola we are, just as the phi coordinate in polar coordinates in Euclidean space tell us where on a circle we are. Whereas the radial lines here of the x coordinate correspond to the radial coordinates in Euclidean space with polar coordinates. They tell us which of those hyperbolae that we are on. So this is an example of curvilinear coordinates in Minkowski space. Now, just to say that in the lecture notes, you will find also an exercise, which is to compute the Christopher symbols, or rather to verify the Christopher symbols. But if you do that, I'm just going to mention the result because we will need it later. You should get that gamma x tt is alpha squared x, and that gamma txt is equal to gamma tx equal to 1 over x. So what I just discussed was how we can introduce now curvilinear coordinates on Minkowski space. And that's not really doing anything. We are still in Minkowski space, so we're still dealing with what is essentially the special theory of relativity. So in general, though, in the general theory, so in general relativity, space-time is a four-dimensional manifold with a pseudometric of signature. You can guess this now, signature 1, 3. So it has one positive direction and three negative direction, one time-like and three space-like direction. And we're also going to impose here the Levi-Civita connection. So just as we could look at Riemannian geometry, so the geometry on manifolds with a positive definite metric, when we go to space-times and we look at the general theory of relativity, is going to be exactly what happened when we went from Euclidean space to considering surfaces and manifolds like spheres and toruses. Just that we go from Minkowski space, which was this affine space with this flat metric, to going to a general curved manifold. So, and everything is going to carry over in the same way. So that's why we spent now 4 lectures on going through the mathematics of calculus and manifolds. So far, I have not said anything about what we're going to, like how we're going to describe these manifolds, but the basic definition is that a space-time is going to be this type of 4-dimensional manifold. So this 4-dimensional curved space in general. So just as an example of a manifold that you might encounter, let's consider the following, which is called the Sitter space. So the Sitter space is a 4-dimensional hypersurface in 5-dimensional Minkowski space. So in order to define a 4-dimensional hypersurface in a 5-dimensional space, we need one relation that is fulfilled. And the way we do this is that we take the following: we take the time coordinate minus, and we square it, minus the spatial coordinates. And remember now, this x here is the 4-dimensional, it's a 4-dimensional vector in the space-like part of this 5-dimensional Minkowski space. And we put this equal to a constant, which I'm going to call x0 squared. So it's negative. So what this means is that if we look here, I can not draw in 5 dimensions, unfortunately, but let me try to draw something. So if we look here like this, and let's take the temporal direction like that, and then we take the x and y direction. So this is going to be 2-dimensional, the Sitter space, which I'm drawing now. If I fix the t-coordinate, so I put this t-coordinate equal to some fixed number, what this is going to say is essentially that this x squared is going to be a constant for a fixed t. So that means that this surface for a fixed t-coordinate is going to be a sphere in those coordinates. So when I draw in 2 dimensions, that will be a circle like this. And as I increase t or decrease, so if t squared increases, this circle becomes larger and larger. So we would have something like this, increasing like this. And the same thing if I go down, we'll get something like this. So if I could draw properly, it would look something like this. So this is the now 2-dimensional de Sitter space. So I have 2 directions, which is essentially one direction going around like this, and which is going to be a spatial direction. So that direction, and I'm also going to have a temporal direction, which is going to be going along the t direction, essentially. So this, yeah, let me say also that the de Sitter space inherits the induced metric from this embedding into 5-dimensional space, which means that since I have these 2 directions, this direction is going to be time-like, this direction is going to be space-like, and so this 2-dimensional de Sitter space that I drew here, or in general this 4-dimensional de Sitter space, is indeed going to be a space-time of the correct signature. It's going to have one temporal direction, and the other directions are going to be spatial. And so this is in essence what space-time is going to be. It's going to be this type of manifold with one time-like direction and the other directions being space-like. So the next question we ask is, how do particles move in this space-time? So the topic is going to be kinematics and test particles. So the assumption here when we say test particles is that these particles do not a priori affect the space-time itself. In general, of course, you know that, I mean, in Newtonian gravity, for example, any mass is going to attract another mass, but we can consider that what we call test particles to have such a small mass that they don't affect the rest of the system. And the idea here is the same. So if we again start by looking at special relativity, I'm going to abbreviate that by SR. We have world lines. So the world lines describe, I can't write now, they describe how something travels through space-time. And when we look at, let's draw that actually. So we have Minkowski space here, we have the time and the x directions. And if I draw everywhere that this particle is at each particular time, I'm going to have a curve of something like this, which I can call gamma. That is the world line of some object. So this just means that at this time, the object is at this point here. At this time, the object is at this point here, and so on. And we just borrow this concept directly from GR. A world line is going to be the path that an object exists in general relativity as well. So in SR, in special relativity, we also introduced the 4 velocity. The 4 velocity, and it is the tangent of the world line. But it's not only the tangent, it is the normalized tangent. So this means that if I take any point here along the world line, I have a tangent vector to that I call V. And in order for, so this is the tangent vector of gamma. And I also parameterize this curve such that the norm of this 4 velocity, V squared, is equal to 1. And in order to be a world line that an observer can follow, I need to have a time-like world line. So the tangent vector needs to be to have a positive norm, and I normalize that to 1. And that again is a concept that we just lift directly from special relativity, with the only difference really that we are now in a general manifold rather than being in Minkowski space. So the question now is, how do test particles move? So yet another concept that we will look at or that you will look at in special relativity is the acceleration of an observer or particle. And in special relativity, you would introduce that essentially as the second derivative of the event vector with respect to proper time, tau. Now, in general relativity, well, let me also say that this is equal to the derivative with respect to proper time of the 4 velocity. In general relativity, we don't have the same luxury. We can't really define this derivative in the same way. Again, for the same reasons we discussed previously, that vectors in different points. So I would be comparing, for example, the 4 velocity in this point with the 4 velocity in a point that is slightly offset. And that's fine as long as we remain in Minkowski space. But as soon as we come to this curved space-time, we can no longer use this definition. So the way to do it instead is to use the connection, the Levi-Civita connection that we have. And we're going to say that the 4 acceleration, write the 4 there, A, I'm going to define it as the derivative, the direction derivative in the direction of the 4 velocity of the 4 velocity itself, or equivalently, the derivative in the direction of the world line tangent vector is the 4 acceleration. Now, this is going to be, when you compare this with what happens in Minkowski space, you will see that it's exactly this definition here as well. This is the 4 acceleration in Minkowski space. So again, it's essentially the same concept, just that this 4 acceleration tells us how much does the 4 velocity change along the world line. And it's essentially the same idea here as well. So with that said, let's also just make another definition, which is the proper acceleration alpha of an observer. That's going to be given by minus alpha squared being equal to the square of the 4 acceleration. So the proper acceleration is the acceleration that an observer will feel. It's what an accelerometer will measure essentially, and that is the metric acting on A and A. And it should be noted that you can show that this 4 acceleration, as long as V is a space-like, a time-like vector. So as long as we have an observer, A here, the 4 acceleration, is going to be space-like, which means that it has negative norm, which means that, that's why we have to put a minus sign in front of the alpha here. Okay. So let's take an example now where we look at the Rindley coordinates that we looked at before. So let me copy that actually. So we had this. So let me copy that here. We had these Rindley coordinates. And so we can ask ourselves, if we fix the x coordinate, so that means fixing which of these hyperbolae that we are on, these hyperbolae are world lines because they are time-like. The tangent vector is always going to be time-like. So we can ask ourselves, what is the 4 acceleration and proper acceleration of an observer with fixed x coordinates. So we're going to put the x coordinate to x0. So that means that the world line is going to be given by x being equal to x0 cos alpha t, and t is going to be equal to x0 sinh alpha t. Now, if I go to Rindle coordinates, I know now that the 4 velocity, since I fixed the x coordinate in Rindle coordinates, this is going to be some function beta that only depends on t times dt. So it's going to be purely in the t direction because the x coordinate is fixed. So if we normalize now, that v squared is equal to 1, we will get that beta squared alpha squared x0 squared should be equal to 1. If you remember this alpha squared x0 squared, that comes from the metric. So v squared is equal to this, where beta here is the time component of v. So this means then that beta is 1 divided by alpha x0. So I choose beta positive such that I go in this direction here along these lines. Choosing beta negative would be that I go in the opposite direction. Okay, so this means that v is 1 over alpha x0 dt, which is going to mean that if I want to normalize, if I want to use a parameterization such that I get a norm, so that I get this normalization automatically, the proper time is going to be tau alpha x0 multiplied by t. That's the proper time along one of these hyperbolae. If I look at the 4 acceleration, I can get that by doing the following. So I take the derivative in the v direction, in the direction of the 4 velocity of the 4 velocity itself. So this is going to be 1 over alpha squared x0 squared. So these are the constants that I take from this relation. And then I have the connection in the t direction acting on dt. And here I can use knowledge about the Christoffel symbols to compute what this is. And what I will get out in the end is 1 over x0 dx, if I do that correctly. So this is the 4 acceleration, which means that I can compute the proper acceleration as alpha squared, that's minus a squared, which is then minus 1 over x0 squared from the components. And then the metric component is minus 1, so I get 1 over x0 squared. Proper acceleration is positive, so the proper acceleration along one of those hyperbolae is constant, and it's equal to 1 over the x coordinate at which essentially this hyperbola crosses the x-axis. So these hyperbolae are hyperbolae of constant proper acceleration, which is also why they are a very common example in special relativity. If you have an observer that is having a constant proper acceleration, you get this kind of hyperbolae for their world lines. So we discussed these concepts of world lines, of 4 velocities and 4 accelerations, and how we essentially just borrowed those directly from their introductions in special relativity. We had to make some slight adjustments, in particular when it came to the forward acceleration, because we could not define this as a pure derivative with respect to the proper time of the forward velocity. But instead we had to use this connection that we introduced earlier on the manifold. So just to mention now that what we will often do now is we will consider the motion of test particles. So what do we know about how particles move in special relativity? I'm going to try to generalize that concept to general relativity. So in special relativity, well, actually also in classical mechanics, you know that if something is not acted upon by a force, so if it's freely falling, it remains in constant motion with a constant velocity. So again, lifting this to general relativity, where we have a more difficult situation because we now introduce things on manifolds, we want to have the forward velocity. If you're not acted upon by a force, then the forward velocity should remain the same, where the same then must be defined by this connection that we had on the manifold. So a freely falling test particle in special relativity, well, that the forward velocity is constant. But that is equivalent to saying that the forward acceleration is equal to 0. So we're going to lift this definition right away to general relativity. And so we have that a freely falling particle or test particle in GR, well, that's going to be defined by the change of the forward velocity, which is equal to the forward acceleration being 0. Now, if you look at this, the derivative in the direction of the forward velocity being equal to 0, this is just the requirement of being a geodesic. This means that test particles, or freely falling test particles, move along geodesics. In space-time. So this is the concept that we are going to use. If something is freely falling in a predefined space-time and its mass is low enough not to alter the space-time properties in any meaningful way, then it's going to move along the geodesic. So this means, of course, that if we look at the special case of special relativity, we get back exactly the property that we started with. That is that world lines of test particles that are not acted upon by a force are just moving in straight lines with constant velocity in special relativity. We can also introduce, just the same way as we introduce forward momentum in special relativity, we can introduce forward momentum in general relativity as just some constant which we call the mass of the particle multiplying the forward velocity. This is the forward momentum. However, so I mean, we could a priori also discuss forward forces, which, as in special relativity, they would be defined as the derivative of the momentum with respect to proper time. But again, we can't really differentiate with respect to proper time. We must use the connection, because for momenta at different proper times a priori belong to different tangent spaces of space-time. So we would have to use the connection, and differentiating with respect to proper time is the same thing then as differentiating in the direction of the force velocity. So we would define the force as the derivative in the direction of the force velocity of the force momentum. However, we will in general not discuss test particles that are acted upon by forces. Most of our examples will be for freely falling test particles, and we will discuss how freely falling test particles move in different spacetimes. So I would like to have time to discuss a few more concepts, a few more physics concepts that we're going to essentially just discuss and lift from special relativity and see how they translate into this language that we have introduced, this mathematical framework in terms of manifolds and four vectors and such things. So the second kind of classical example of something relativistic is the relativistic redshift of light, for example. So that's the next thing that we will discuss is redshift, or of course in general it could be a blue shift. Let's just say it's a frequency shift of, well, a wave, for example, light. So the first thing to think about is what we actually mean when we say a frequency of a wave. So frequency is something that relates to how the phase of a wave changes with respect to the time of the observer. So let's just make a quick drawing here. If I draw a wave like this, the phase function here, if this is a normal sine wave, so I would have a phase function phi. It would be equal to 0 here. It would be equal to 2 pi here and 4 pi here and so on. Now, when this wave moves, if I am an observer standing here at 0 and the wave moves to the left here, eventually I'm going to end up with a phase value of 2 pi. And the time it takes to do that, so if I'm standing here as the observer, the time it takes for this point on the wave to reach me, so the time it takes for me to reach a phase value of 2 pi is one period of the wave. And so the frequency of the wave is 1 divided by that period. So another way of saying it is that the frequency is the change in the phase function phi per proper time of the observer. And now generally this phase function is going to be a function of space-time. So if you just consider the typical sine wave, we would have the wave itself being something like sine ct minus x, something like that. So this would be a wave moving in the x direction. Now the phase function, well, we would have an amplitude here, and we would have a phase function which would be this function inside of the argument, right? And the frequency would essentially, well, let's mix up angular frequencies and frequencies a little bit. But the phase function would be this phi, this argument of the sine function. So this is a function of x and t, so it is a function on space-time. And the question of what is the frequency of this wave, well, it's a question of how much the phase function changes per proper time. There's probably some, this is not really dimensionally consistent. Let's put it like this. We have omega t minus lambda, well, lambda inverse x. That's the phase function, which should be dimensionless. Okay, so now comes to, so this phase function is a function on space-time, and it's going to be the same also in a more general space-time, not only in Minkowski space. We don't know what the phase function is, but we know that what we define as the frequency is how this phase function changes with time. You see that if I just differentiate this, if I stand at the same x, so if I fix x and I remain at x equal to 0, we see that the derivative of the phase function here with time is going to be omega, the angular frequency of this wave. So it is indeed the change of the phase function with respect to the proper time of the observer. So the question is going to be, if I look at the world line of an observer, how much does the phase function change when I increase the proper time of the observer? So the question is, how much does the phase function change as the proper time of the observer increases? So essentially, what I'm asking is that I have this world line and I have this phase function which has these level curves. These are level curves of phi, and this is the world line of the observer, gamma. And so the question is, when I change the proper time here, what is the derivative of phi? So phi dot, which is the phi, the tau, that is what I'm going to define as the frequency of this wave. But if we just use the chain rule here, this is the chi, well, I'm not going to write it dk, let me write it with dots. This is chi dot a, where the dot represents derivative with respect to proper time, dA phi. Or if you so will, this is this chi dot a, that's just the components of the forward velocity. So this is the forward velocity acting on this phase function phi. You can also write it as d phi, where d phi is now the differential, so it's a dual vector acting on the forward velocity in the language that we introduced before, right? So the frequency, which was just the change of the phase function per proper time, can be written like this in terms of the forward velocity and this phase function, the differential of the phase function in the manifold. So this means that if I know the forward velocity of the observer and I know the phase function, then I'm going to know which frequency the observer observes. Let me also just introduce what is called the for frequency n of the wave. That's the tangent vector corresponding to this d phi, just that I raised the index. So I'm going to define NA as GAB dB acting on phi, which then means that the frequency f, well, that's the inner product of this for frequency n and the forward velocity of the observer v. Now the question is, what happens when we make this wave? So I didn't really require anything from the phase function so far. But what I want to do now is to consider light-like phase functions. So what this means is that I want to have phase functions whose force frequency is light-like. So this means force frequency light-like. For example, a light wave. So if you consider a light wave, so that would mean that we have something, well, in Minkowski space, this would mean that you would have something like a phase function would be phi equal to omega t minus x divided by c, for example. Or if we're going to continue using c equal to 1, just t minus x. This would be a light-like phase function because if you take this d phi, that would be omega dt minus omega dx. Then you would find that this d phi has a square of 0 and is therefore light-like. So essentially any light wave is going to be of this form. Also when we go to the general theory. One can show then, I'm not going to go through the explicit computation of this, but the explicit computation is written in the lecture notes. So it can be shown that if you do this, then the derivative in the direction of the force frequency of d phi is going to be 0, which means that as long as you're following the these light-like paths, which are defined by, which are essentially the integral fields of the force frequency. So you go along the world line essentially of a light pulse, then the phase function, or rather the differential of the phase function is going to be parallel transported along that path of the light. So what does this mean for observers? Well, let's consider the following situation. So let's take an observer here. The observer is generally going to move along some world line. But let's say that this observer at this event, so let's call this event E1, is going to emit a light signal. And we a priori don't know how that light signal goes out, but the tangent vector of this light signal, or this path, is always going to be this n. And at some later point, we have another observer here. So this is O2, and we had an observer O1 here. And at this point, so E2, this observer O2 receives this light pulse. So the question is now, we emit this light signal at E1 with some frequency. And the question we can ask is, what frequency will O2 observe at this point, or at this event E2, when the light signal reaches him? So the way of doing that is that we know the observer O1, we know the force velocity, as long as we know how O1 moves, and we know what the force frequency is going to be when this observer emits this, this light pulse. So the frequency here, f1, that's going to be the inner product of n and v1, so the forward velocity of observer 1 when they emit this light pulse. From this condition, we also know that the phase function, or equivalently n itself, is going to be parallel transported along the path of this world line. And also note here that this is equivalent to that n itself is parallel transported, which means that this path that the light signal takes is a light-like geodesic. So this is the frequency observed by observer 1, but once we get to this event 2, we're going to have an n which was parallel transported from event 1 to event 2, but we're also going to have the forward velocity of observer 02. And the frequency that this observer observes is going to be the inner product of the fourth frequency at that point with V2, the fourth frequency of that observer. And in that way, we can establish, given f1, we can establish what is the frequency observed over here by the second observer. So this was all rather theoretical. So let's take an example of this. And then we come to questions. So the example, which hopefully is going to be a little bit more hands-on. Let's consider the Doppler shift in Rindle coordinates. So we discussed previously these observers which had constant x coordinates in Rindle coordinates. So we will now consider a light signal sent from x equal to x0 at t equal t equal to 0 to x equal to x0 plus delta x, where delta x is some constant. Well, we take delta x small. And we ask ourselves, given that the frequency for the original emitter is something, we want to know the relation to that of the second observer. So assume now that for the first observer, that is equal to some basic frequency f0. When we ask ourselves, what is the frequency observed by the observer at x equal to x0 plus delta x. So the first thing to know, I mean, we're now working in two-dimensional Minkowski space with Rindle coordinates. So we know that any 4 vector can be described as, in particular n then, as some constant there, well, some component before the t and some component before the x. We also know that v1, we checked this was 1 over alpha x0 dt, because this was an observer at a fixed x. And we computed the forward velocity of such an observer earlier. So this means that f0 here well, let me do the following first. We know that n, the 4 frequency, is going to be light-like. So n squared should be 0. So this is going to give us some relation between these components, right? So we had the metric nn. If I call this alpha and this beta, this is gtt alpha squared minus gxx beta squared, and that should be 0. This gtt I knew was alpha x0 squared. This gx plus gxx is minus 1. So this is going to tell us something about the relationship between alpha and beta. In particular, it's going to tell us that beta is alpha x0 squared, sorry, alpha x0 multiplied by, now I have 2 alphas. So let's call the second one gamma instead. Gamma, right? If I also insert the following, so that we know that V1 in a product with n, that should be the frequency F0, that gives me directly then the value of gamma. So this gives that n is going to be equal to F0 divided by alpha x0 dt plus F0 dx at x0. And I know the sign here because I want it to move in the positive direction if I assume that delta x here is small and positive. So now that I've done that, I can actually repeat the same argument for or rather I can repeat this argument here with n squared. I can repeat that anywhere along the world line of this light. So the world line that the light-like geodesic that the light signal follows. And that means that I am going to be able to write this this 4 frequency generally as 1 over alpha x times some function of t, and let's call it, we can actually call it f of t. And let's take that one out. Let's do the following. Some function f of t dt plus dx. So the only thing I have done now is that I have required that this 4 frequency be light-like. So it's essentially this requirement applied to any point. And then I have just chosen the functions along this world line such that I can get this f of t out. Okay. So using the parallel transport equation, I can now insert this into the parallel transport equation, and I can figure out what this function f of t is. So inserted into the parallel transport equation, so that is to say that we want this to be equal to 0. This is going to give us a differential equation for this function f. And what we're going to find out, if we do it properly, the math is in the in the lecture notes is that f prime of t plus alpha f of t is equal to 0. Now this is something you can solve. It just means that f prime is some constant is some constant times f itself. So f as a function of t is going to be f0 e to the minus alpha t, right? So this is essentially the solution. And the only thing left to do is essentially to figure out what t this light signal crosses the second world line at. Anyway, what we will find out is that the observed frequency for observer 2, well, that was the inner product of this 4 frequency with the 4 velocity of that observer. So that again is the inner product of whatever we had here. I'm going to just write n. It was what we had on the previous page, and the 4 velocity of the observer 2 is 1 over alpha x0 plus delta x dt for just the same reasons. So this is going to actually pick out the t component of this 4 frequency, which was essentially this, right? So this is going to be equal to 1 over alpha x0 plus delta x, and all of this squared because I have it also here. And then I have an f0 e to the minus alpha t from the solution to f. And I have the metric component gtt, which was alpha squared, and then x0 plus delta x squared. And we now see that this cancels this. So what we are left with is going to be f0 e to the minus alpha t. Any questions on this solution? So what we know here is that this frequency f for the second observer is going to be related to the frequency that the original observer emitted. So f divided by f0 here is e to the minus alpha t. So depending on whether this is larger than or smaller than 1, well, it's going to be, let's see, smaller than 1. So we're going to have a redshift because the frequency becomes smaller. Any questions on that computation? I feel as if I have talked a lot. Okay. So that about redshift. I mean, the general, if you look back at the special relativity case with redshift, you can actually also convince yourself that this is actually the same kind of arguments we have for what redshift is in special relativity as well. And in general, we're going to be able to argue this type of red or blue shift in different ways. But everything is in the end going to boil down to this kind of argument. This is kind of the more general argument for how you would compute the frequencies observed by some observers. So unless there are questions, let me come to the final concept that I wanted to discuss today, which is the concept of simultaneity. And what it means for something to be simultaneous. So if you're familiar with the special relativity case, I mean, that's when we have Minkowski space again. So we would have the x direction, and we would have the t direction, and we would say that in this coordinate system, in this coordinate frame, simultaneities are the lines with constant time coordinates, or with some fixed time coordinate. This could be t equals to t0, t equals to t1, t equals to t2. We say that two events, A and B, they are simultaneous in this coordinate system if they occur at the same coordinate time. Now you also know that if I change the coordinate system, so let me take the following coordinates. That's a very light gray. Let's take something darker. If I change my coordinate system, so I now have instead the t prime and the x prime axis in the prime system, the simultaneities are no longer these lines that I already drew. Instead, they are the lines that are parallel to the x prime axis. So it's instead going to be those kinds of lines, which then correspond instead to t prime equals to t0 prime and so on. And we say that two events are simultaneous in the prime coordinate system if they have the same prime coordinate time. So in this case, A and B would certainly not be simultaneous in the prime coordinate systems. However, in general, there is nothing stopping us from choosing any coordinate system. Indeed, you saw the example of Rindler coordinates earlier on Minkowski space. So when we talked about simultaneities in special relativities, we often refer to simultaneities defined by Minkowski coordinates. But in general, nothing stops us from choosing some arbitrary coordinate system. So I could a priori choose a coordinate system which has some time-like coordinate, but it has some fixed coordinate surfaces that looked something like this. They would still be space-like curves, but they would somehow, in some sense, in that coordinate system, define what it means to be simultaneous. So in order to say that something is simultaneously, we consider any coordinate system where the metric is on the following form, so ds squared, some positive function. Well, I can actually normalize it. So I can normalize it so that I have dt squared there, and then minus, well, some something here, dt the x, where x contains the other coordinates, and then plus something additional that is essentially a metric, a space-like metric on the hypersurfaces that are of constant t. And I could say that two events are simultaneous if they occur at the same t. Now, this doesn't mean much because we could essentially choose, well, if not arbitrarily, but rather freely, we can choose from different coordinate systems. It would actually be sufficient if we can find a set of hypersurfaces like this, like these ones, that make up the entire manifold. That would be sufficient to say that I just label those hypersurfaces by different time coordinates, and I would call anything that falls on the same hypersurface to be simultaneous. So any definition of simultaneous is going to depend on what coordinates we have chosen. And therefore, just as in special relativity, in general relativity, the concept of simultaneity is not a very strong concept. It's not a very generally well-defined concept either. However, it should be said that in some cases, such as in cosmology, there are some standard choices of coordinate systems. And in those cases, it's going to be clear what we mean by something being simultaneous, because we're going to have chosen this this convention of simultaneity to mean exactly something that most people will understand if you say that. So just the final thing here, the same thing as simultaneity does not really hold a very well-defined meaning in general relativity. The distance between two events also does not hold a very well-defined meaning, because you could imagine the following. Let me take two world lines. So let's take two world lines, and let's take two events. Now, you could say, I want to know the distance between those two events. Well, unless they are simultaneous, distance does not really mean much. However, if you have a simultaneity and you say that those two events are simultaneous, so this would be corresponding to t equals to t0, for example, I could measure I could define the distance between those two events as the spatial length along this simultaneity between the two events. However, that is still not very well defined, because there could exist a different simultaneity which might look something like this. And then in that coordinate system, the distance would be d2, because it's along a different hypersurface. But again, in some standardized cases, such as in cosmology, we have kind of standardized what coordinates we use. And so we have also standardized some of those notions of what distance means when we refer to it. So in general, it's better to just look at the light cones, just as in special relativity, to look at the light cones and split the space-time into, if you have a given event, you can split the space-time into the past, to the future, and elsewhere, or spatially separated. From this event P.